All right, so the notebook that we are gonna work on today is in notebooks, SAR training, English, UNAFCO core, UNAFCO InSAR, MintPy tutorial. In this folder, you have two notebooks, small baseline app and small baseline app ARIA. Please make sure that you are choosing small baseline app ARIA because we are gonna use the ARIA product for the time series analysis today. And I would like to acknowledge Yun Zhang, who has been the main developer for MintPy last few years. And he has contributed a lot to developing this notebook too. I hope he's online. We asked him to be available today. The idea is, as I said, there are many products processed by ARIA, and you have already run ARIA tools, and you have cropped and stitched the product. Now they are ready for time series analysis. So I'm gonna just go ahead and run the first cell, and feel free to go ahead and do the same, which basically download the stage data from S3 bucket, and otherwise it's like 400 or 500 interferograms, and we don't really have time today to download it using ARIA tools and then run ARIA TS setup. But basically, it's essentially just two lines really. Later you can try it yourself with a different area. So the download is still going on, and at the end, if everything goes fine for you, you have to see this message which says S3 pre-stage data retrieval was successful. All right, so we are good to go ahead. Before starting, we need to set up a configuration file for MintPy, basically to tell MintPy what are the inputs and what are some of the minimum processing parameters. MintPy is primarily consistent with ICE outputs. However, as you will experience in this session today, it's consistent also with ARIA products, and some users have contributed SNAP. SNAP is the processor from ISA for processing Sentinel-1 data. So if you have those interferograms, there are MintPy should understand them. Gamma, somebody has contributed, and ROIPAC also is supported. There are many options of the configuration, and I will show you that in the documentation. Yunjun has done an amazing job in organizing the documentation. It's very clear, just even looking at the configuration file is very clear what each option is. For example, the first one, mintpy.load.processor, in our case is ARIA, the update mode. Many of the options have some default and some other options that if you want to choose between, and there is an explanation of auto means, which is a default. And for this case is yes, which means if you have some time series from before, then you want to replace it and update it. The compression that you want to use for if the data was downloaded from ARIA, or if you had ICE process data, if you want to use any compression, because we are saving the products in HTF5 files for MintPy. And a few other options that actually are not relevant today, because if you would have processed your stack of data with ICE, then you would just give the path to the folders that you had the unwrapped interferograms there or different files. You can specify a reference point for your time series analysis. Remember that all interferograms that we are processing are differential observations in time and in space. So those unwrapped interferograms, they have been processed separately and they have different reference pixels. So we have to reference them to the same reference pixel. MintPy has, if you don't specify anything, MintPy will look at the average spatial coherence and chooses a point that is coherent through time. But if you know your area and you are familiar with your data set, like what I did here, I was familiar with the data set, so I already give a reference pixel, just the latitude and longitude. And different correction capabilities like tropospheric delay correction using the PyAPS, ERA5, ERA-Interim, and few other models. Topographic residual correction or DM error correction is supported. You can remove a ramp from each interferogram or time series if you want. And unwrapping error correction, which we will get to. Right now, we are setting all the corrections to no. So we just want to take the stack of interferograms and simply do an inversion. And we will get to the error analysis after that. So run that first step, and there are many more configurations. And if you click on this link, it will take you actually to the GitHub page where Yunjun has put together a very nice configuration, all the parameters, and very clear explanation of what each parameter is. A lot of questions that you might have later could be already, the answers could be just in this configuration file. And there is a paper that at the top of the notebook, there's a paper about the software itself. And to my knowledge, this was the first paper in our community that probably all the figures could be reconstructed using the Jupyter notebooks that Yunjun has made them available publicly to everyone. So whatever figure you see in the paper, the data set is available and the notebooks are available, you should be able to reproduce. So very similar to our ICE applications, you can just say small baseline app.py --help. That's the main application that we are going to use today, which from the name, it's very clear that it's very similar to the SPAS method. It's a least square inversion of the unwrapped interferograms. With, of course, it's a modern version of the SPAS. And while we are going through it, we will talk more about it. Dash help just will show you the help message. What are the different steps that one could use while processing the data with MintPy? Loading data, modifying the network, reference point, introducing reference point, a quick overview, which is a simple stacking without doing any fancy inversion, correcting phase unwrapping errors. Inversion, that's where you go from the pairs of interferograms to phase through time, which is your time series, and different correction steps, which we will get to. I will go ahead, and that's the configuration, but since we have a simple function to configure it, I will just run that cell, and that creates in the directory that you are, it will create a San Fran, which the data set is over San Francisco, Sentinel-1, the track 42.txt, which the content is really just these few lines of the configuration for MintPy. Once we have that, let's go to the next step, which is loading the data. And since we are using the stage data on S3 bucket, then you should see this message that the data is just staged and we already have it. And the only folder that is created right now is this folder inputs, which has two files, ifgramstack.h5 and geometry.h5. The ifgram stack, so all the interferograms from ARIA after running ARIA tools with the bounding box that we have specified, now they are in the interferogram stack. Remember that these two files were already available on S3 bucket. And if you don't want that, then you have to turn off the use stage data at the top of the notebook. And then you will see that there are two commands for running, actually these two commands here. ARIA download.py will download the data, and ARIA TS setup.py, as Simran and David have explained to you, will prepare the data for the time series analysis. And we have already done that, so we have the inputs. So let's just take a look at these inputs. We have this very useful info.py command that tells you what is inside each of these HTF5 files. Apparently, there are some metadata and some data sets, perpendicular baseline, the coherence, connected component files from unwrapping, a data set for the dates, because these are pairs of interferogram, unwrapped phase, that's the main data set that we are going to use. And there is this data set called drop ifgram. That's a Boolean data set that specifies which interferogram to be used for unwrapping, because we have some capabilities to modify the network, but for that we are not modifying the actual data, we are just flagging them to use them or not. Right now we are using all of them. And there is the geometry file. If you take a look at the geometry, it has azimuth angle, height, incidence angle, slant range distance, and water mask. And those are produced either by ICE or water mask, maybe by ARIA tools, but they are all available for you, and they are on the everything is on the same grid. Let's take a look at the network that we have. You guys already explored that with ARIA tools. Now, MintPy also allows you to look at the network. What are the interferograms that you have? That's your baseline plot, perpendicular baseline through time. And here is the coherence matrix. What Piyush showed that this matrix is basically image number by image number. Since we are using small baseline interferograms from ARIA, the coherence matrix is not full. As you see, we have only some nearest neighbors and some annual pairs. And the color is just the average coherence for each of the interferograms. Some more statistics of the coherence for different pairs through time, and time baseline plot of average coherence of all the interferograms. Basically, each dot here is one SLC acquisition date, and each line is one interferogram. The color of the line is the average coherence for that pair. Very similar plots probably you saw in the ARIA tools demo. Go ahead and generate a few more masks. The first one is the average spatial coherence. We have a stack of interferograms. We have actually 443 interferograms, and we just want to look at how the spatial coherence looks like, just average all the pairs through time. For those of you who are familiar with the area. This should look very familiar. This is the Bay Area, where we have San Francisco somewhere here. And those who are familiar with the tectonics of the region know that San Andreas is here and Hayward Fault is here and a few more faults. We will get to it. Just to look at the water mask, what we have, and a mask of the connected components. Each unwrapped interferogram comes with one connected component. We can look at each pixel through time now that everything is on the same grid and come up with a mask that tells us which are the pixels that always have a valid connected component. Basically, the connected component more than 0 is valid, and whatever is 0 is not valid. So these are the pixels that have value, reliable value, in all interferograms through time in the unwrapped files. Since we have reference point already specified, we run the next step. As I said, each interferogram has a different reference point. Now we want to make sure that they are all referenced to the same coherent pixel. By doing this, actually, we are not changing the data at all. We are just adding an attribute to our interferogram stack, and that is understood by MintPy during the time series analysis. Let's take a look at what happened. All happened is adding the reference point to the HDF5 file, which you can take a look at. And that's exactly the reference point that we introduce in the configuration file. All right, let's do the time series analysis and invert the interferograms and get the time series. So basically, at this step, all we are doing is inverting the pairs of interferograms, unwrapped interferograms, with a least squares estimation, very similar to the original SPAS method. We are not using any new functionalities yet for this simple inversion. However, please note that MintPy supports different weight functions. So the original SPAS doesn't have any weight, it's uniform, but you can specify different weights. We will get there. And you can modify the networks, different corrections can be applied. Right now, it's doing a patch processing. Since it was a large data set, it divides to different patches, and we are at the patch of 5 out of 6. 6 out of 6. Okay, so not too bad. It took only 1 minute and 11 seconds for 400 interferograms, 443 interferograms actually. Of course, it's a small area. The size of the data set is not too big. And the results of this inversion is a file called timeseries.h5, which we can just take a look. Info.py timeseries.h5. It says that there are 100 acquisitions here, and these are the acquisition dates. These are the acquisition dates in decimal, in years, and few different attributes that might be used later. The HDF5 has one data set for the perpendicular baseline through time, and one for the dates, and one for the time series itself, which basically is the result of the inversion. Okay, so I see that Yunjun is online. That's good. He's taking care of the questions. And let's take a look at what's inside this time series actually. And if we take a look, we should, there is this very useful script in MintPy called view. You can call it from Jupyter like this, or in a terminal you can call it just as view.py, and it has many functionalities to display different data sets. Here we are displaying all different acquisitions through time, basically the time series. So the reference is the reference date, and there is a reference pixel somewhere here. So this is just a general overview of what happened, and each acquisition now is referenced to the first date. Now that we have
it's cumulative.
It is a cumulative, yeah,
Okay.
cumulative displacement. It's not still, I wouldn't call it displacement, but once we do the time series, it's already in meters. The plot shows centimeter here because that's the default, but the unit of the what is in the time series, that H5, is in meters. And basically it's a rain change time series, and it's inclusive of atmosphere, any geometrical residual, or actual ground displacement, because we haven't done any correction yet. Now that we have the time series, let's go ahead and estimate rate of the time series and take a look at it. That would be the next step. It's already done, and you can take a look at the velocity. All right, so we have our velocity field from the time series. This is for the Bay Area. So in the previous years, it was in person. It was not all virtual. So we had a nice interaction. I would like actually to ask that. We have time. We are not behind. So what geophysical signal do you guys see here? If anybody is familiar with the area, with the tectonics of the area. Hayward fault, yeah, Hayward fault is there. So do you see strike slip behavior? Yeah, some strike slip. Yeah. What specific signal is very evident? What specific signal on the Hayward fault is evident? Yes, Chelsea, yeah, thank you. Okay, I know you know that. And topographic correlated atmosphere, it might be, we haven't done any atmospheric correction, but actually it's not very evident to me. In this specific example, actually, what I see is more signal, and you clearly see this is the Hayward fault, and there is a very nice discontinuity from blue to green. By the way, that block box there, that's our reference pixel that we introduced at the very beginning. To be honest with you, when I processed this data set last year, I didn't know the data set, so the reference pixel was chosen to be somewhere, I don't know, here maybe. It was a coherent pixel, but I wanted to be here. So because I knew my data set, I knew it's coherent because I had done the time series once, and I wanted to see this discontinuity immediately. So that's how I chose my reference point, but it's relative, right? Once it's chosen, you can actually change the reference point and the rate map too. And yeah, thank you, Mylene. We will get to that line. That's an artifact. I assume you are referring to this one. Yes, yes, let's let's look at the signals first. So there is a very clear tectonic signal. It's a fault creep and the Hayward fault, very well known, and we already see it. Since it's a creep at surface or close to surface, it causes discontinuity. There is some also faulting here, and also some hydrological signals. By the way, this is descending track, and we are looking at line of sight. So whatever is red color is moving towards the satellite, and whatever is blue is moving away. We are looking at San Andreas fault and North America and the north east with respect to the Pacific plate. So what we expect is Pacific moving northwest, and that's what exactly the direction of the rate map makes sense. Because if that's your reference pixel, the blue is moving away, so it's moving this way, and that's consistent with the plate motion, and red is moving this way. So in a relative sense, the colors make sense. Some of the signals are there. One other discontinuity is here. That's also Calaveras fault. There is a creep on that fault too. And San Andreas here is locked. We don't see creep. The total red to blue roughly also makes sense. We know that the plate motion here is around, the total motion is around probably, Garrett, correct me, it's around 4 centimeters per year probably.
Yeah.
And we are capturing most of it actually here, because if you project that 4 centimeters per year in line of sight direction, you will expect, given the Sentinel-1 incidence angle, you would expect something around 15 millimeters per year, and that's what we see roughly, without any quantification. Those are just and there are really more signals. I mean, this is not, to me, atmosphere 2. There are hydrological smaller signals. But there is this artifact as well, as some of you guys noticed already. That's not a fault cape. We know our data is descending, so most likely, and we know it's Sentinel, so we know Sentinel has bursts, and that's very well consistent with some burst boundaries probably. So we will explore that in more details. But before doing that, that will be the other half of the session. Let's take a look at this velocity estimate comes with some misfit of the rate estimation. It's not very meaningful. We are aware of it. For example, it doesn't really capture that artifact. And the uncertainties are very optimistic here. It's only the misfit. We are aware of it. That's what we are really working on. Yunjun specifically and UG at JPL are working on this problem. So hopefully we will end up with more realistic uncertainty maps. But we have some qualitative measures to explore artifacts like what we saw here, and specifically more unwrapping errors and the quality of the inversion, which we will go through those. But before getting there, since we have time, I would like to take a look at the chart, and if there is any questions. Yes, 90-meter posting. Yes, these are standard area products. They are 90-meter posting. Yes, okay, so I see Piyush and Yunjun and Garrett are active there, so probably you guys don't need me.
So can I ask a question, Harris?
Sure.
Just to clarify, if we didn't use ARIA inputs because they don't exist, where we're working, for instance, the options would be to use either TopsMap or StripMap app, but have it, geocoded to the same location, or use the stack processor. Is my understanding correct of that?
That is right, yes.
Okay, so all of those options work for getting it into.
Yes, yes. As far as it's on the same grid, it should work.
And do you also just have to feed it? I mean, I know from Giant, you point it to, your set of directories that are labeled with the start and the end date, and it pulls all the data out of that. Would you give it something similar?
So yes, something similar. Let me go to the configuration file, or maybe actually I will just pull up this notebook, small baseline app. This one is based on a different data set in Galapagos, which Yunjun has processed using the stack processor. And here, the loading is different. The processor is ICE. The meta file is one of the XML files of your reference. We should actually change this to reference. And where the unwrapped file is, you just say wherever the interferograms are and some star and field star.unwrap. The correlation file, the connected component file, where your geometry file is. So basically, you just tell where your files are. It's most consistent with the stack processor, but it should be really very easily, maybe somebody already has done to fit the TopsApp outputs too. But we don't have any trapping. The assumption is your interferograms are on the same grid.
I was just wondering about the accuracy. If we're not using a stack processor and we're just doing pairwise processing, you mentioned somebody mentioned earlier that if we were doing something that was to a millimeter kind of, if I'm looking for a really small signal, will it be accurate enough without co-registering or using the stack processor? I'm using LS data, so
if you our recommendation is definitely use the stack processing if you care about 1 millimeter per year stuff. Actually, just recently we haven't published or presented, but yeah, we have observed phase closure due to pair processing itself. So it could be improved through some better pair processing, but the existing pair processing of multi-looked and then geocoding, it will result to some, I'm talking about 10-20 degrees phase. I'm not talking about 2 pi. I'm talking about 10-20 degrees phase. So it's really the impact. I even don't know what's the impact on the time series yet. We haven't gotten there yet. But yeah, the recommendation is to use the stack processor. Make sure that everything is consistent through time. Keep that consistency from SLC all the way to where you are going, if you care about small signals.
Can you adapt the stack processor for ScanSAR, or would I just align the SLCs and then? Maybe not relevant.
The stack processor for ScanSAR is actually under development right now. Shunran at Caltech started this, I think, last week. I don't know when it will be available, but it will be available. One of the nice things about stack processing is, as you guys noticed during this week, one of our most time-consuming steps is topo or RDR2 geo computation. If you do pair processing, you have to do that computation for each pair. If you are making 1,000 pairs, you have to run topo 1,000 times. However, if you do stack processing, you run topo 1 time. And that's one of our most time-consuming processing steps. So besides accuracy stuff, there is also advantage in going to the stack processing, if possible.
So just to follow up on that, because I'm actually not familiar with the stack processor at all, but can you still process, from interferogram to the sequentially through the dates, or does it all go back to the same reference file?
Yeah. So Yunjun will demo that in the afternoon. Yeah,
Perfect.
you can
Okay.
specify if you want only next neighbor pair, or you want 2 nearest pair or n nearest pair. You can specify that.
Okay.
Yeah. All right. So that would be the notebook for that, and I'll just show the visualization notebook. So in the same folder, UNAFCO InSAR MintPy tutorial, there is a visualization folder. If you guys look at that visualization, there is one that has the TS view that IPYNB, and we have to actually modify this path. So let me just quickly in a terminal just to make sure that where we are, notebooks, course, MintPy tutorial, and that's where I could just relatively point to that's where I would like, if you guys want to do use this notebook for the time series viewer on the OpenSAR lab, you have to do this modification actually. The path was wrong. And this one will be just time series.h5. So that's the path that we were working on, and that's the file time series.h5 that we want to look at. So run the first cell first, and then the second cell. And it shows the time series. This is actually from Giant originally, that Piyush wrote. The viewer is from Giant. And you can just look at each date, see the time series. If you go far, probably it's noisier. Closer to your reference pixel, there is a slight ramp, which is due to the trip. And it's less noisy because you are closer to the reference pixel. And we know that the dominant noise is atmosphere, and atmosphere is spatially correlated. So closer to the reference pixel is less noisy. So this is the viewer, and you can drag this to look at different epochs. It's not the best viewer, but that's what we have right now. Has many functionalities I like. However, it might be slow for large data sets because right now it loads everything into memory. That can be easily changed, really. So yeah, you can play with the time series yourself. Just to be clear again, to get it to work, you have to change the path to where you were working. It should be actually similar to what I have. And change this file to time series.h5. The rest should be fine.